So yesterday we looked at how populations grow and how populations can change and how to figure out or calculate that population growth. But now what we're going to do is we're going to look at kind of what's the limits to that population growth, because a population just can't grow forever and ever and ever. Obviously there's predation, predators, or lack of food or disease or all sorts of things that can affect that population. So we call that kind of that limit to the population growth carrying capacity. And that's kind of your largest population that an environment can support. The environment can only support so many organisms in a population. So eventually we're going to reach that carrying capacity and it's not able to carry any more of that population. It's the capacity of organisms the environment can carry. The carrying capacity is affected by all sorts of different things, and it's affected at different times since it's affected by factors like resources, weather, predators. Like it depends all the time. So you might have like a really good a year for berries because maybe there's lots of rain and lots of sunlight, and then there's lots of berries in the bush, so there's lots of deer or bears or something feeding on them. So those bear populations, the environment can carry them more, but maybe the next year you have a bit of a drought and the producers aren't growing as well and they can't support as many individuals, so now some of your population starts to die off. So it depends on the year, depends on all sorts of things. Now your population of any organism will fluctuate. It goes up and down all the time, and that's just kind of follows that carrying capacity. But you kind of get this average where that's kind of the average that the environment can hold, or that ecosystem can hold. And if we draw a line through the middle of those fluctuations, that actually represents what we call our carrying capacity. So you'll see a really typical curve for a population. So let's look at what a curve for a population would look like. This is that logistic curve that we talked about yesterday. So you're going to see the rise, and you're going to see this rise at the start, and then you kind of get above the carrying capacity, so the population drops, and you get below the carrying capacity, so the population can rise again, and you get this rise and fall and rise and fall. If we draw a line right through the average of that, that is what our carrying capacity would be. So the population will always have ups and downs along that carrying capacity line. Now, it's also useful to consider how many organisms there are at different ages in a population, like especially if we're looking at the human population. So for example, if we know how many people are at different age groups, so like if we think of young children, and then we think of young adults, and then we think of kind of middle-aged adults and senior citizens, we can actually look at the population of those different age groups and figure out whether our population is going to rise or fall. We can draw these out as a histogram, which is basically a sideways bar graph, and you've probably drawn stuff like this in math class. So we'll put age along your vertical axis, and then along the horizontal axis will be how many organisms or how many there would be in that population. And usually we have one side for males and one side for females. And again, when we're talking about males and females, in this case we're talking about genetic males or females, because we're looking at reproductive abilities, right? So if there's very few females, then we can't have very many offspring. If you have few females but lots of males, then you're not going to have lots of offspring. In lots of environments, like if you're thinking of fishing, I'm thinking of crab fishing, they're not allowed to keep females. They're only allowed to keep males because the females are the ones that can actually carry the young, and that would affect your population if you dropped your population of females, because you can have many females carrying babies by one male. So when we're looking at an age population histogram, it shows a snapshot of the organisms, both male and female, that fall into the categories of age. And this data is represented for an instant in time. So that shape will allow us to predict what kind of population, whether the population is increasing, decreasing, or remaining steady. So here's an example. This would be an increasing population histogram. So we're looking at an example where we have lots of males and females at the bottom, but we don't have very many towards the top. So the bottom of the pyramid is big. Now, what's going to happen with this population is the young individuals are eventually going to become into the reproducing age, and they're going to be able to have babies. So that means that soon this population will increase because you have more people in the young age group. So again, if we look at this population, the young are going to become reproducing. They're going to make more young, and that's going to make the population grow over time. You'll notice that generally speaking, the number of people decreases as you move up, because there are people that are going to be dying at all age groups, and that's just a reality. But if you have a larger base of this histogram, then that means that overall the population will be rising. Now, if we have a population that looks like this would be a decreasing population. So this means if we look here, this is your reproducing group of people. So the ages of let's say 20 to 40. This is kind of your reproducing age. There's lots of people here, but they're not having many children. So they're actually having less children than there are people that are able to have children. So that means your population is going to drop. Now, because it's wide in the middle, that means your population is going to drop, because these reproducing people aren't replacing themselves. If they had they were having babies about the same amount as there are in the reproducing age, then our population would stay pretty much consistent. But because they're having less children than there are reproducing people, our population is going to be dropping. So it's like, if I go back one, I'm going to go back one. So if we look here, the reproducing people are having more children, right? So it's like most of these people are having, let's say if they're couples, they're having 3 kids, maybe 4 kids, right? At least 2 kids, because they're at least replacing themselves, if not more. Now, in this population, though, these individuals are having less kids. So they're having maybe 1 kid or 2 kids. So they're only either replacing themselves or having less, or maybe having no kids. So that means that there's not going to be as many young to replace reproducing, which means that they're going to have less young. So your population over time is going to drop. Now, if we're looking at a steady population, you'll see that it's mostly kind of almost straight up on both sides. And that's because your reproducing people are having slightly more young than the reproducing number of reproducing organisms, because some of those young, like in any population, some of those young, like if you're talking about ducks or something, they might get eaten by a predator or something like that. So you need to have a few more than like some extra babies to help sustain your population, because you will lose some over time. But at least they're replacing themselves. So because you're replacing yourself, you have a pretty steady graph here. So the numbers are quite steady.